And we're back. Welcome back and happy Thursday. Today, we will pivot to neural networks, yet another type of linear model. But before we begin, let's pick up where we left off with a little bit of a refresher. So we talked about logistic regression, and in that, we talked about cross-entropy error had some desirable properties. It is a convex function, and convexity is important because it is very amenable to gradient optimization, but it also means that it is not susceptible to initialization problems. You can initialize your weight vector, and by following the gradient, you're always going to find the global minimum. We also covered the logistic regression algorithm after developing our expression for the gradient, and the most appropriate gradient is one that's self-scaling. It's proportional to the distance from the global minima as captured by the size of the gradient. So if you're further away from the global minima, it will be larger, take a larger step. As it starts to get closer and closer to zero, our gradient, it's going to make smaller steps. Okay. We also highlighted how by making very simple changes to this modest linear model, whether it's the algorithm, the expression for pointwise error, or the search method, you can get very powerful behavior out of a very modest linear model. Okay, so let's look at a variation of gradient descent for logistic regression, the so-called stochastic gradient. Now, gradient descent, our expression for in-sample error, ran in so-called batch mode, where we computed En using the entire data set of size n, and we got our expression for the cross-entropy error. In essence, for logistic regression, our pointwise error was this ln of 1 plus e to the minus yn w transpose xn, where we look at the coincidence between the unknown target function in the ground truth class label and the score w transpose x in constructing the target probability, which originated as a product likelihood. And so in this, we iterate over steps along the gradient of the error, the gradient of En, and the minimum was negative if the direction v hat, as we said before, was opposite the direction of the gradient, and it's going to decrease our weights, our steps. And so our delta w was minus eta, our step size in the direction of this gradient based on its magnitude, gradient En, for current working hypothesis W. Now, of course, our gradient En was computed from all of our in-sample data, our label instance pairs, xn, yn, and this is called running in batch mode or batch gradient descent. Now, you can do this stochastically. Instead of over all of your inputs, you can do that by randomly selecting one of your in-sample points and its ground truth label and perform gradient descent on pointwise error instead of batch error. So for some randomly chosen point, you would look at the expectation of this gradient of the pointwise error, and so that expectation is over our inputs and their corresponding labels. The expectation of the negative of that gradient for the pointwise error is then just 1 over n. The sum at n goes from 1 to big N of this negative gradient for the pointwise error. Now, of course, if you take that average, you get exactly the batch mode error gradient. And so this is called stochastic gradient descent, and it has some desirable properties. You get different noise depending on the randomized value that you select, and the noise averages out over time. Now, this stochastic gradient descent is more efficient because it's cheaper to compute instead of over batches of data over individual sample. It's randomized, and it's also simple. And so the rule of thumb generally is that your learning rate eta, your step size, is usually about 0.1. And we made the assumption that this is a convex error surface, but in reality, error surfaces are not so straightforward. They're typically very complex, like we see here, the inset on the right-hand side of the screen. Now, what this stochasticity gives you is the ability to escape shallow local minima, because now you're kind of jiggling the weight vector through this randomization, allowing you to escape local minima, that problem we talked about with that depiction of the complete error surface. And that is what is more typical of error surfaces. And so stochasticity, in addition to being cheaper to compute, this randomization gives you the ability to escape local minima, trying to find the global minimum. Okay, so just so happens that the Netflix prize that we talked about early in the semester, the winning solution was a variation of stochastic gradient descent. So the method is very, very powerful. So let's take a look at neural networks, the main subject of today. And so neural networks are bio-inspired. And with any kind of bio-inspired method, you're trying to mimic something in biology in terms of the basic form, but then you use engineering to realize it. On the left-hand side, we have a sheet depicting some neurons under a microscope. On the right-hand side, we have that engineering analog. We have axons, we have dendrites, we have synaptic connections. The output of one neuron is the input of another in some geometry. And so a neural network is basically inspired by our biology in terms of the basic structure of a computation, what it's doing. But then from there, you use engineering tools in order to realize it. So the whole idea behind neural networks concerns the combining of perceptrons. And so here, in the upper left-hand corner, we have some perceptron, H1, and we have H1 over a data problem, and this hypothesis can generate a dichotomy where you have the plus side of the line and the minus side of the line. Conversely, some other hypothesis, we can shatter this data set. We have 2 points, the minus side and the plus side. But if we have this complex problem, we'll call this the exclusive OR problem. Well, in order to produce this particular dichotomy for these 4 points, we can't do that with a single perceptron. We know that the breakpoint of a perceptron is 4. So if we combine perceptrons, we can produce more complex dichotomies beyond what we're able to with just a single perceptron. And so we can take these perceptrons and construct logic gates, and we can aggregate these gates to solve precisely this exclusive OR problem. And it's exclusive OR, but in this case, we're going to call a Boolean 1 a plus 1, and we're going to call a Boolean 0 a minus 1 label or output. And so if we take the following configuration, we have our inputs x1 and x2, and this third input, you can think of that as our dummy variable x0, but we're going to give it a different term. We're going to call it a bias. And so this particular configuration, we have a hard threshold, and our OR is going to look at the sign of the weighted sum, these inputs times the weights associated with these edges. And so here, we're going to look at when x1 is plus 1, x1 is minus 1, x2 is plus 1, x2 is minus 1. Now, going with a gate, logic gate, interpreting plus 1 as a Boolean 1 and a minus 1 as a Boolean 0 or binary 0, let's look at what this OR function is. So OR says when both of them are binary 1, the output is 1. Otherwise, if one of them is 1, the output is 1. But if both of them are 0, the output is 0. So at least 1 is a binary 1. So let's look at this, test this out. So we have a case where, let's say both of them are 1. We have 1, and 1 is our input. 1 times 1 is 1. 1 times 1 is 1. 1 and 1 is 2. We add 1 times 1.5. 2 plus 1.5 is 3.5. Sign of that, it's positive, is going to be plus 1. Okay. Let's take it when one of them is 1 and the other is minus 1. It doesn't matter which one. We have plus 1 and minus 1, that's 0. 0 plus 1.5, sign of 1.5 is going to be positive, so it's 1. Okay. Let's look at when they're both negative. Well, we have negative 1 times 1, that's minus 1. Negative 1 times 1, that's minus 1. Minus 1 and minus 1 is minus 2. Minus 2 plus 1.5 is negative 0.5. Sign of negative 0.5 is minus 1. So that is exactly the OR function. Let's look at this AND function. What AND means is that both of them must be 1 in order for the output to be true, to be 1. Okay, so in the case where both of them are minus 1, that's like a binary 0. That's minus 1, that's minus 2. Minus 2 and minus 1.5, minus 3.5, sign of that is minus 1. Okay, so when one of them is positive, that's 1 and minus 1, that's 0, plus negative 1.5, that's minus 1.5, sign of minus 1.5 is going to be negative, so minus 1. Okay, so let's look at when both of them are plus 1. That's 1 plus 1, that's 2. 2 plus minus 1.5, that's positive 0.5, sign of positive number is going to be 1. So it acts just like an AND. So this is going to be our OR function using the inputs and our weights, our perceptron. This is going to be the AND function. These configurations give us this logical function. So we can now take different hypotheses and we can combine them. Now the XOR is saying H1 ANDed with H2 bar. And when we look at negation, negation is using an edge weight that's a negative 1. So H1 ANDed with H2 bar, you OR that with H1 bar ANDed with H2. So this is going to be an OR, just like we saw from before. It's an OR gate when this bias weight is positive 1.5. When it's negative 1.5, it's an AND gate. So if we were going to construct this exclusive OR using the perceptron, here we have our hypotheses, H1, H2. So this gate is going to be H1 ANDed with H2 bar. So we have H1 with a positive weight, H2 bar, so H2 with a negative weight. It's ANDed, so this bias weight is going to be minus 1.5. Likewise, here we have H1 bar ANDed with H2. So H1 bar, so H1 through a negative weight, negative 1, ANDed with H2 with a positive weight, okay, that's 1, and is ANDed, so that's going to be a negative bias weight, negative 1.5. So now we're going to take these and we're going to OR them together. So we have an edge weight 1 here, and we have a bias weight of 1.5. That's the ORing of these two functions. And so when we look at these hypotheses, we can expand these hypotheses as being a weighted combination from an input vector x. And so here we have W1 times x. We have x2 here, so we have our weighted sum, x1 times its weight, x2 times its weight, and we have our x0 fixed to 1 times our W0, which is our weight, our bias weight. And so here's our x1, our first hypothesis. Here's our second hypothesis, W2 transpose x. And now these are our hypotheses. What we're now combining, this is H1, this is our H2, and we're combining them through the XOR version of our multi-layer perceptron network. So this is the H1 bar H2, and this is the H1 H2 bar. Let me make sure I have that right. H1 H2 bar, H1 H2 bar, H1 bar H2. Okay. So this is a so-called two-layer network, and the first layer implements H1 and H2. The second layer implements the terms that you input into the XOR, and this is the OR for some output. And so with multiple layers, you can do more to shatter a data set than with a single perceptron. And so when you construct them, they're in a stylized fashion. There are no backward links, and there's no skipping layers. So we don't skip from this input past that first layer to the next one. So what can you do with multiple perceptrons? You can take a simple model and make it very complex. Suppose we had the following target function. You have radially arranged geometry. All the +1 points are closer to the origin in feature space, and all the -1 points are further away. Well, with 8 perceptrons, you can produce that dichotomy. You can shatter that data set. Now, with 16 perceptrons, you can get much more sophisticated, closer to that circular decision boundary. But the problem is, as you go up in perceptrons, you start to increase in the number of parameters, because remember, we have 2 parameters, W1, W2, plus that bias term. So it gets very unwieldy, and as we saw, you pay for that complexity, that increased size of the parameter space, with needing more data, because the hypothesis set is larger, has a larger VC dimension. And so one of the things that this also gives us is, because of these hard thresholds, it's also very difficult to optimize, to find the final best hypothesis, because this sign is nonlinear. It's really hard. So one of the things we can do to fix this is to change the threshold from something that's a hard threshold to something that's smooth and differentiable. And so this is a so-called neural network, and a neural network consists of an input, and it could be images, it could be tabular data, what have you. We have a number of layers, and these inputs in stylized fashion compute weighted sums, and these weighted sums are input into nodes at a given layer through a smooth differentiable nonlinear function. And so we have our weighted sum plus our bias term at each layer. And so when we look at our input, we call that X, our hidden layers. We're going to number from hidden layer 1 up to hidden layer L -1. Now this big L, you notice here you see a less than sign. L is going to be designated for the output layer. That's where the output h of x, our compositional nonlinear function, computed by this neural network. Now this output layer is big L, and we use little l to index and identify the hidden layers, and then this index L is big L, corresponding to the output layer. Now, one example of this nonlinear function theta, sometimes called a squashing function, one example is the sigmoid. Also, the hyperbolic tangent is a popular choice, tanh. So let's go through a description more generally of a neural network. And I'm going to kind of habituate over this, because it's really, really important to understand the notation in order to understand how we compute the outputs compositionally, ultimately leading to h of x, which is the hypothesis, the working hypothesis. So we talked about the nonlinear function, and this is the form for tanh, hyperbolic tangent. And this hyperbolic tangent is a mix between a hard threshold and a soft threshold. If the score input into tanh, the weighted combination, the inputs times the weight vector, is closer to 0, well, tanh, we're in this region, and it acts like a soft threshold. It's linear. But if we get further away from origin with our score, to the left or to the right, tanh looks a lot like a hard threshold. The hard threshold is in the red. Tanh is either +1 if you have a large positive score, or -1 if you have a large negative score. But if it gets closer to origin, it looks more like this linear threshold. And so tanh interpolates, if you will, between a linear threshold and a hard threshold. It's so you can think of it as softening your hard threshold. So we have our weight vectors, and the weight vectors stand between a layer to the left a lower level layer. Let's call it L minus 1, and the layer following it, layer L. And so the outputs of the previous layer, we're going to call that X for layer L minus 1. And these are going to serve as the inputs to some other layers, nodes, at layer L. And so when we talk about the individual weights, and these edges correspond to the weights, we're going to talk about the input using index I, the output node using index J. So this is the input node. They are combined by weighted sum. And this is the output node at the next layer. We're going to use index J when we refer to one of these output nodes. Now, when we say weight vector, we are going to identify the layer corresponding to the weight that we're referring to. And so this weight can be associated with the first hidden layer, the next layer up to and including the output layer node. So that output layer node is going to be here, and that's going to be our H of X. And so when we talk about weight vector ij superscript L, well, L indexes over the layers. Which layer is it? Okay, so it's layer L minus 1, layer L, so forth, and this is layer big L. When we look at this index I, that subscript, index I is going to identify the input node, and that input node is going to be for the layer before L. And you see here, I goes from 0 to D superscript L minus 1. D superscript L minus 1 is the dimensionality or the number of nodes for the input layer beneath layer L. And so when we refer to weight I, it's going to be the weight vector from a particular ith input node to a particular jth output node at layer L. So then when we talk about J, J is the index describing the output layer node, and you notice its dimensionality goes from 1 to D superscript L, the dimensionality or the number of nodes in layer L. So when we say W ij superscript L, it is for layer L, node J, the weight that goes from input node I to that node J in layer L. Okay, so now when we have these weight vectors, we end up with a matrix. And this matrix, when we look at the rows, that's going to be the I, and these rows correspond to the input node, and the columns, J, correspond to the output node. The superscript is going to define a different plate, if you will, that corresponds to the weights for each layer. And so you note that the dimensionalities can be different from one layer to the next. So that means you would have one matrix for one layer. Maybe the matrix would be bigger for another layer. Maybe it would be really small for another layer. And this is the W ij superscript L. And in fact, when you look at deep learning network frameworks, they call the popular technology is called TensorFlow. A tensor is a generalization of a matrix. A zero-dimensional tensor is a scalar. A one-dimensional tensor is a vector. A two-dimensional tensor is a matrix. And so it's called TensorFlow because it's a framework for computing these tensors, and it takes these partial results and sends them to other tensors as you compute these compositions of weighted sums. And the weighted sums are matrix vector products, where the matrices correspond to these weight vectors. Okay, so let's look at how you compute a particular output in layer L for the jth node. That's just our nonlinear function, tanh, evaluated on the score associated with node J in layer L. So that score is the weighted sum of all the inputs before. And if we expand out what that score is, that's just the sum. For input 0, that's going to be our dummy variable, x0, the bias term. I goes from 0 to the dimensionality of the input layer, which is a layer below, L minus 1, or the layer preceding, layer L minus 1, that's dimensionality, all the input nodes. Weight Wij from node I in layer L minus 1 to node J in layer L, and we're going to use that weighted sum, that weight, we're going to weight the output of that ith node from layer L minus 1. So we're going to sum together all of these. These are the xi superscript L minus 1s, and our weighted sum here, we're going to use Wij, these are all the weights, and we're going to take that weighted sum and input that to this nonlinearity associated with that particular jth node, which is our squashing function, in this case, tanh, hyperbolic tangent. So you note the output layer at layer L is always formed in terms of weighted combination of inputs from layer L minus 1. And so we have layer L minus 1, we have layer L, and we always take a weighted combination. These are all the Wij superscript L's for that jth output node. And here are the I input nodes. Okay. And so when we take this network, defined thusly, we start with an input X and we apply that to an input layer. That's our input layer. It's considered the 0th layer. It's not a layer from the network. It's a layer taking the inputs. You can think of your input as a layer, the 0th layer. And so we take our inputs, and that's of dimensionality D superscript 0, dimensionality of layer 0, which is just the dimensionality of the input. In deep learning, this could be a vector, it could be a cuboid, it could be an image frame, it could be a lot of things. We apply this input, computing the output for layer 1, and then we take the outputs of layer 1 and make them inputs to layer 2, layer 3, and so forth until we get to layer big L, which is the output, which is our result for the current working hypothesis. Now, of course, for this, our current working hypothesis is a complex function, and all of the weights correspond to all these matrices for all these layers are going to be the parameters for this complex hypothesis. So it is a type of linear function at each layer that is weighted combination passed through a nonlinear function composed, again, another weighted combination passed through a nonlinear function. And it's called the forward pass when you go from the inputs through those layers, one at a time, 1 through big L, to get your output of your hypothesis, the working hypothesis H of X. Okay, so let's end there. And with that, I will see you all on Tuesday.